This is 7th of August 2024, and this is a DCCS, doubts clarifying and calculation session. It could be a follow-up to a thesis byte, and this is a follow-up to second thesis byte on conformal algebras. So what I'm going to do is clarify a few things in the conformal algebra part. So that means I will be focusing on these, this, and all the red and purple ones, violet or purple. Yep. Yeah, purple and red ones. These. Right. So some of these, most of these actually. So I am also stressed since some time now. I don't know why, but I just feel overwhelmed by a lot of things, just day-to-day things. But I think I'll just be kind to myself for now. Being kind in the sense, I just realized I was suppressing my emotions instead of letting them come and gently letting them go. But yeah, I've been suppressing them and moving forward, which is a bad thing. And I just decided now to just let them flow, and then letting them go is a better option. And that's why the tone of my voice right now is in a very calming way, I guess. I don't know. It's letting go tone of me. Interesting. So yeah, and also this is it is 5:30 right now. 5:33. This is my meditation, okay, exercise, okay, relations wala time. But I couldn't do the thesis work today, so I want to first do that, and then I want to give time to some other things, because I've not been able to work on thesis. There's a lot of time, and need to prepare for the next meeting with my advisor. So, and yeah, as I said, I haven't been maybe able to function properly because of many reasons, which I'm trying to slowly understand and take necessary steps, I guess. But yeah, yeah, this is the truth. I'm not doing so well in that sense, but no need to worry. I'm just admitting it. Yeah, I know I can take care. Yeah. So this is a session. This will be a very kind session in resolving some of the doubts in conformal algebra, so that I can, yeah, there's nothing called so that. I just want to understand a few more things. So yeah, there's also this other thing ki I'm probably focusing too much on getting things done and showing up to someone, or to some class, or to someone, rather than enjoying the subject truly. That has been missing. I mean, it's hard to expect that, but it's okay. I mean, since I note that now, I can do something to fix that. So yeah, this will be a slow session. I want to just spend a couple of hours at least on thesis. So yep, I'll also set a timer somewhere. I don't know. I think I'll use the focus. So I want to focus for 2 hours, and don't remember the break duration. Music please. So after 1 hour I get a 5-minute break. Interesting. I need a 10-minute break for this. So let me just focus clock. Yeah, I don't really care recording all those, because yeah, I don't really care about that. So what I need to do is settings, focus periods, break period. Let me just make it 10 minutes. Maybe I'll have a slice of bread or two. Yep, done. Now I want to start to, so wait, settings, just for 3 seconds, focus periods. I want 2-hour period. What? Okay, yeah, 1 hour. Yes, that's fine. That's fair enough. Wait. Reset. 120 minutes. Yes, you'll have 1 break. Yep. And please don't play any songs, because I have my own songs. No, I don't have my own songs. It's fine. I'll just put this here. Okay. I think this is fine here. Oh, okay. It's only visible. Just set it here. Yep. It's alright. So yeah, I'll start now without much delay. Yes, let me get some water, of course. Cool, let's go. So the first part is the basics of conformal transformations. I don't recall having any major doubts in that, but I'll give it a check anyway. I'm sure I have some. I don't know. So conformal transformations, yeah. So yes, there is a statement. Okay, so I need to write this down, right? For class, so I need to put myself. So the first thing I want to ask him is about the statement that was made in wow. Okay, so just give me a second. Of course, sure. Then we're back. So, yep. So, what I was talking about is written in. So, the statement about how the going to light cone coordinates and complex coordinates in use of string theory. Yeah. D equals to 2 conformal. D equals to 2 conformal transformations. Complex light cone coordinates. Light cone coordinates. Complex coordinates and string theory. Second out will be about, yep, yeah. So okay, I haven't written here. So one is about um, string theory equals to 2 light cone complex chords in string theory. That's the right. And then there is at most quadratic solution to conformal condition for Kelvin condition. Cool. So the first one I'm leaving it to Sir. Okay. I don't know which color. Hello, maybe. I'll ask Sir about it. Almost quadratic solution to conformal Killing condition. Okay, so this is where I'll start using the la. So the doubt is xi mu should satisfy conformal Killing condition, which I won't write, but upon solving reasonably and simplifying things, especially for no, not especially, yeah. Wait. Yeah, for flat metric simplifying and all that, what you get is this condition for the conformal Killing vectors. So this is the condition that you obtain in the end, which needs to be satisfied. It's not a sufficient condition, of course, it's one of the conditions. So does this imply xi can only depend quadratically on x? Is a question. So the condition says the second derivative of del dot xi is 0. So what do you mean? Del dot xi should be a linear in x? Linear in x? That's what it says, roughly. Then that means if del dot xi is non-zero, then at most linear in x, so xi is at most quadratic in x actually. In x, or else doesn't vanish. Yeah. That's the rough conclusion, and that's why you fix xi to be all the things that you already knew, because it translation, Lorentz transformation, dilatation, and conformal transformations. Okay, so I mean, the book that I'm following is rough statements actually. It's not very precise, I guess, but still, good intuition given things. So just thinking the b mu, x mu, and a mu together, they are isometries. Okay, and isometry doesn't fucking change the metric form. So omega is 1. Omega is not even dependent on x in that part. So these are automatically here. This must be here. So yeah. Here is quadratic in x. That's fine. Roughly again. So this is almost green. So yeah. So what else thinking? So yeah, roughly you are clear, yeah. This is again the problems. If you want to look at the whole everything again from beginning to summary kind of thing, we'll end the session with that maybe. Okay. Now there are many problems, and we'll get to those and solve those. Yeah. It's hard to do everything in one simultaneously, right? Good. So next out is this: interpreting the SOD algebra. Okay. First term, fixing the rest by antisymmetry argument. Okay. So this goes back to our, oh, that's so in the beginning. So it is okay, apparently I know the page number, so 72. Cool. Now the interpretation of the Lie algebra. Okay. So it's this here, interpretation. In the interpretation we have that there are three sort of symmetries, yeah, Mn, PQ and Mn and PQ too. So the definition of Jmn itself says that it is antisymmetric in Mn and if you interchange Mn, you get a negative of that. Cool. So cool. So thing is that it's completely fixed. Okay, yeah. So the terms is completely fixed by the first term by noting that the left hand side is antisymmetric under the three separate interchanges ms to n, p to q, and mn to pq. So we have to analyze this. So the thing is, the first term we have is MP and J and Q. Okay. I mean, we can derive this, yes, but we're just trying to interpret it. So the first term gives the rest of three terms. How do you prove that? Let's say you interchange M and N. then P and Q. To change P and Q, we need a minus sign, right? You need a minus sign to whatever you got previously, right? So assume the first term is a non-zero 1 in beginning, and then now you interchange P and Q. You should get the negative of whatever you used to get. So what was the MP and NQ? So you just write MQ and NP, but with a minus sign, right? But why is there a plus sign? I don't get it, man. I don't get it, honestly. If you replace M and N, then sure, you get a minus sign. In fact, if you replace the whole thing, M and PQ, even then you get minus sign. Only if the P and Q involved is changing, you get a plus. I don't know. I don't want to. I mean, I don't know, man. I'll ask this to a friend, maybe. Yeah, this is a very logical thing, I guess. Ask a friend. So that would put me this into some color of which color should I ask? Which color speaks of friend? No, actually, no, I can't go back. Actually, again. So I don't know. Maybe a cyan. Maybe no. Maybe an orange. Maybe a yellow hand. No, maybe an orange. Yep, orange. Yep. Okay. So this thing. The first का कुछ हुआ है. Ask friend. It's a simple thing. And this is something very impressive thing. I mean, two boosts generating a rotation. That's crazy, right? When you think of it. I mean, two boosts. I mean, why is the commutator relevant? Is because when you apply two different boosts, you are applying two different boost kind of transformations infinitesimally to a vector, and then you apply the inverse of that also. Sorry, thing is, you apply two different transformations. Exactly, you apply two different transformations of two different boosts basically. You apply two different boosts, and just see whether if you apply them twice continuously, and does that commute with applying in different direction. Turns out, if you apply boost twice, it differs by rotation. Exactly, it differs by rotation. Exactly. That's what it says. Right? Two boosts applied in a different order differ by rotation. Now, this leads to something called Thomas precession and spin-orbital coupling in atomic physics, and I would love to see how this whole thing sets it into the atoms, molecules, and radiation could be done in a very group theoretic way, properly symmetries, Rothenberg symmetries. Right? But I won't delve into this now. Let me go to identifying conformal algebra on d-dimensional Minkowski space with a SOD2 algebra. This is important. So the claim is that in a d-dimensional Minkowski space you have SOD d minus 1 comma 1, right? And the conformal algebra of this space is we identified it. The conformal algebra of this space has we counted, and it turned out to be d plus 2 times d plus 1 by 2, half of d plus 2 times d plus 1. This turns out to be the same number. I mean, the number of generators of conformal algebra in a d-dimensional space is half of d plus 2 times d plus 1. This turns out to be the number of generators of SOD, 2 group algebra. SOD, 2 D algebra. So now we are identifying. In fact, the claim is that the conformal algebra of d-dimensional Minkowski space-time with Lorentz group SOD minus 1 comma 1 is the Lie algebra of SOD D2. SOD2 is isomorphic to conformal algebra d-dimensional. That's the statement. What's the proof? It's a very wavy, hand-wavy proof. All we know for now is the number of generators are same. Okay, I need to really get a new book, man. ऐसे नहीं चलेगा ना. So what was the reasoning they are trying to what is that? You know. So it's back to conformal algebras. Yeah, identifying the conformal algebra. We can prove this assertion by what else could it be argument. The only uncertainty is the signature. So I mean, I don't get it, dude. You have to show that these generators are actually the generators of SOD2 isomorphic. अच्छा, okay, what do you mean by group isomorphism? The Lie algebra isomorphism? Yeah, algebra isomorphism is that you preserve the operations, right? Preserve the generator operations between them. I guess you preserve the commutators eventually. Sort of. Do you? I don't know. First, of course, the generators, number of generators have to match. Then all that. No, this is the approach is not right. So, conformal algebra and the isomorphic group. So I mean, this gets interesting because if you consider a n plus 2 dimensional space, ADS is n plus 1 dimensional. The um, the isometric group of ADS n plus 1 is SO is what? SO comma 1. No, SO, I guess it's 2 8. Yep, SO 2 comma n. Wow. Turns out, okay, yeah, sure. Yes. So turns out SO2 comma n is the isometric group of ADS n plus 1. Now, what do you think ADS n plus 1 ka boundary is n dimensional, and n dimensional space में conformal group is nothing but SO to n is isomorphic to SO to n. So that's how conformal groups are the isometries of ADS n plus 1 on the boundary of ADS n plus 1 become relevant to the conformal transformations in that boundary. I mean that's how connect, but that's why it's crucial to understand this isomorphism, right? It is crucial to understand the isomorphism between conformal algebra and Lie algebra of higher dimension. What? The isomorphism between conformal algebra and Lie algebra of higher dimensional variable. But seriously, okay, leave that. Let's go back to this. The algebra of SOD2. Conformal algebra of d-dimensional vector space is this. One dimension of SOD minus 1 is the Lie algebra of SOD2. Okay. Since you need to match the generator, see, the whole approach of this problem is weird. In this book, of course. I think let's just study the conformal algebra. Conformal algebra notes or whatever. Maybe, yeah. Mm-hmm. Yeah, the question is how are you saying these two algebras are isomorphic? See, if I go to mathematics, then to go different, but I need to find balance between both. First, I need to go code. So structure, I mean, see, SOD comma 2 Lie algebra. What is SOD comma 2 Lie algebra? Wow. What's the Lie algebra? Lie algebra is S2. I mean, if it actually matches, then it would be great. And signature we have to fix here. SO2 D comma 2, dude. How can you just write that statement that is disagreement? Wow. Seriously, can you try to find out the SO2 D comma 2 Lie algebra? What you need is generators of this algebra, right? What is this? What is it's nothing but the metric is the D comma 2 signature, right? You take D and then minus, I mean, it's basically the sum. It's basically the sum. It's basically sum I equals to 1 to D xi square minus x xd plus 1 square minus xd plus 2 square. You need matrices of transformation that preserve this metric, right? SO2 comma 1 we had Lorentz transformations. SO D comma 1 or D minus 1 comma 1. How did we do that? Well, the same this formulation, right? I mean, it should be irrelevant whether it should be irrelevant of signature. You just write eta mu of any signature, the algebra will be same. So all have the same Lie algebra, honestly, same structure. It has more generators. I mean, the number of generators vary, but point is, even SOP comma Q has the same algebra, then same Lie algebra, as well as SOP. So any SOPQ has the same Lie algebra. Is that true? structure is same, but the dimensions are different. The number of generators are different. But now when you're comparing the conformal algebra, the generators are matching. How do you know that the real algebras are matching? Well, we know both the real algebras. What is a conformal algebra? The conformal algebra is a set of 6 three dimensions. Very good. Sorry, screw that. Conformal algebra is given by the commutators between all these generators, which is this. The whole of this. So, how do you compare this with a simple algebra of the SOD equal 2? How are you saying these are isomorphic? Yeah, I mean, is there a way to combine all these into a single parameter, single generator index, and write it in a general algebra? Then that would become a real algebra, right? Yeah, I need to ask this to my fellow friends or sir again. This is beyond me, man. Ask sir. And then first term fixing rest. Ask friends. Then third doubt is this. Identifying conformal algebra. Well, algebra D dimension. SOT, 2. Okay, I mean, yeah. Does this go? Deepak or Sajjad mostly. The other ones are working in this direction. So, then we have the much awaited light cone coordinates. For God's sake, let's clarify what light cone coordinates are. Okay. Cool. Light cone coordinates. Okay. light cone coordinates was introduced in this very book. So it's just to decouple the time and space part. That's what I know. Okay. X plus minus is t plus minus x, and it somehow decouples. No, it doesn't decouple. Let's see. Simple. Wikipedia has a statement about what it does, where two coordinate axes combine both space and time, while all the others are spatial. Yeah, I see. Yeah, why light cone coordinates are important? Let's see some examples. So in special relativity, two of the coordinates are null vectors and others coordinates are special. Okay, special. Okay, the former can be denoted with x plus minus. Yeah, that's right. We are logging in the d comma 1 here in signature. Instead of standard coordinate systems, yeah. So instead of having this, you have delta ij dxi dxj with I comma j equals to 1 and so on to d. Okay, now this becomes in light cone coordinates minus 2 dx plus dx minus plus delta ij dxi dxj. So dt square you will just roll as dx plus and times dx minus. So what's the use? Well, I do too. Fine by me. X plus minus are called time coordinates. Fine. Call them what you want. Significance. One nice thing about light cone coordinates is that the causal structure is partially included into the coordinate system itself. Oh, so okay. A boost in T explain shows up as the squeeze mapping, a rotation in IJ by only effect explode. So okay. Light cone coordinates sometimes calculations by using light cone coordinates. See Newman-Penrose formalism. Light cone coordinates are sometimes used to describe data equation. In string theory, the closed string and a generalization of spatial coordinates with string is conveniently described by parameter sigma and general string. Appropriately described by parameter sigma 0 associating each point. Okay, so here how did it enter here? It was through the conformal generators in the light cone coordinates. Yeah. Yes, here. I simply wrote it this way. We had two dimensions, so there are no spatial coordinates, no other spatial coordinates. So we just have simple this, and we just evaluate all the conformal generators, right? P, D, K, J, and everything in the differential operator form. Interestingly, we had these. Okay, so we constructed Penrose diagram for M and reducing compact variables. So its causal structure analysis करने के लिए use किया गया था. Fine. Light cone coordinates. Okay, that's a bit of context around it. How in my project, where do I use it? I need to ask sir, right? Yep. Yeah, so there's that. Light cone coordinates are clear, but the contextual relations, contextual significance, relevance has to discuss this further. I think, yeah. Wow. Alright, so causal structure analysis is easy over. That's what it says. Yes, one nice more one. Causal structure is partially included into the coordinate system itself. Interesting. How did this happen and all that is something that we need to do a lot of study, right? For now, I just did some rough study. Okay. So apparently, using this again, you can make more, find more compact variables and um, construct Penrose values and sort, which I don't know. Let's not go there yet. Okay, fine. Okay, this will be more or less done. The how are light cone coordinates relevant to us is a question that we need to hold on to. Contextual relevance. I don't know, man. Yeah, I think I should just green. Yeah. And when we use the correct coordinates, we get it right. It's fine. What do we have here? Angles and conformal transformations. How are those related? I want to see a YouTube video or conformal transformations and angles. Angles? Angles? What angles? Shit. How are conformal transformations related to angles? I don't know this. Yeah? I mean, in relation to conformal theory, through the looking class of conformal symmetry. Maybe I could see this video.
Today we're going to talk about conformal symmetry. Conformal symmetry is a fundamental notion in conformal field theory, which is one of the most active fields of theoretical physics today. One experimental use is in modelling many body systems at the critical point when they're between phases of matter. Probably the most famous appearance of conformal field theory, or CFT, is as the latter half of the ADS CFT correspondence proposed by Malvicino. This correspondence is so celebrated as it models both quantum and gravitational effects, and a theory of quantum gravity is one of the main goals of modern theoretical physics. Another application of CFT is string theory, and string theory is also where many of the ideas in conformal field theory originated. While string theory may no longer be a popular theory for modelling our universe, the study of string theory and CFT introduced structures which drove breakthroughs in mathematics. So what is conformal field theory? In brief, it's a theory, a physical theory, which has conformal symmetry. You should view this as an extension of the fact that the laws of physics largely don't depend on where you are, what time it is, and which direction you're facing. Restated, the laws of physics have space translational symmetry, time translational symmetry, and rotational symmetry. So what are the transformations that a conformally symmetric system is invariant under, also known as the conformal transform? Restated, there you are, what as an extension of the fact that the laws of physics largely don't depend on where you are, what time it is, and which direction you're facing. Restated, the laws of physics have space translational symmetry, time translational symmetry, and rotational symmetry. So what are the transformations that a conformally symmetric system is invariant under, also known as the conformal transformations? You'll get slightly different answers depending on who you ask. A mathematician would say something like an angle preserving transformation, while a physicist might be more likely to say a symmetry of a scale invariant system. Actually, scale invariant systems are quite a strange thing to consider. Consider Alice, who is a scale invariant girl living in a scale invariant world. By virtue of being scale invariant, Alice can scale up by a factor of 2, and she shouldn't experience anything differently. Now let's think about the stress exerted on her shins. The equation for stress is force divided by area. In this case, the area is the cross-sectional area of her shins, while the force is her own body weight, which is proportional to her volume. We can find how these scale with some characteristic length scale L of Alice, such as her height. Her volume will scale as L cubed, while the cross-sectional area scales as L squared. So the stress exerted on her shins scales proportional to her own length scale, which is going to be pretty painful as Alice grows large. The only way Alice can escape this is if she is in fact massless with zero density, which feels like an unfair body standard to hold Alice to. So even everyday macroscopic physics is scale dependent. So we're going to talk about conformal transformations as angle-preserving transformations, and see how scale invariance comes out of that. And we'll start with the hold Alice to. So even everyday macroscopic physics is scale dependent. So we're going to talk about conformal transformations as angle-preserving transformations, and see how scale invariance comes out of that. And we'll start with the simplest case, angle-preserving transformations in 2 dimensions. We can't just use 1 dimension because there's no angles. And the nice thing is, all the transformations that you learn as a baby preserve angles. Translations, nice. Rotations, nice. Dilatations, nice, we'll take that. The rotation and dilatation here were centered at the angle, but in fact you can rotate or dilate about any point and you still get an angle-preserving symmetry. And by the way, dilatations are just a fancy word for enlargement, but make it more clear that shrinking is allowed as well. At this point, you might be wondering what transformations don't preserve angles, so you graduate from kindergarten and start thinking about skew or shear transformations. For this particular shear, the unit vector in the x direction and the unit vector in the y direction start out at a right angle, but end up at pi on 4 radians apart. At right, unit vector in the x direction and the unit vector in the y direction start out at a right angle, but end up at pi on 4 radians apart. There are lots of funky transformations which are also not angle preserving, and in fact the vast majority of 2D transformations do not preserve angles. Pretty remarkably, one can show that those transformations from earlier, translation, rotation, and dilatation, as well as their combinations, are the only conformal transformations of the whole plane. That is, the only invertible transformation from the plane to itself that preserve angles. You might be wondering why reflections are excluded, since they look like they preserve angles, but they only preserve angle magnitude, but they flip the direction of the angle. Within this group of transformations generated by translations, rotations, and dilatations, we can restrict only some of these transformations to find other, perhaps more familiar transformation groups. For example, restricting to translations and rotations only, then the transformations don't just preserve angles, but also preserve length. And these transformations are called isometries. Dilatation obviously doesn't preserve length, and that's the real novelty of conformal symmetry. Just to emphasize this point, if rescaling is a symmetry of your system, then equivalently, the system has to be scale invariant. If we instead restrict to rotations and dilatations about the origin, we get linear transformations, which can be described by matrices. Invariant. Your system, then equivalently, besides this point, if rescaling is a symmetry of your system, then equivalently, the system has to be scale invariant. Free of your system, then equivalently, the system has to be scale invariant. If we instead restrict the rotations and dilatations about the origin, we get linear transformations, which can be described by matrices. However, translation is not a linear map, so we can't describe it by a matrix. Surprisingly, if the symmetry are extended by some extra transformations, called special conformal transformations, then the set of transformations generated by rotation, dilatation, translation, and these new special conformal transformations turns out to be the symmetries of space-time, with 3 space and 1 time dimension, and these can be described by matrices. Okay, but I said earlier that the transformations, without these new special ones, are all the conformal transformations of the plane. So these extra symmetries turn out to come from what's called a conformal extension of the plane. The rest of this video is going to be about why and how we can do this extension, and the extra structure this extension buys us. The way that we extend the plane is by adding a single new point to get a sphere. We can see how this works by folding up a disk. By increasing the radius of the disk, the gap in the sphere closes up, so that in the limit that the radius goes to infinity, we get the plane, and then only a single point is needed to plug up the gap. The way that we extend the plane is by adding a single new point to get a sphere. We can see how this works by folding up a disk. By increasing the radius of the disk, the gap in the plane. The rest of this video is going to be about why. The way that we extend the plane is by adding a single new point to get a sphere. We can see how this works by folding up a disk to get a sphere. We can see how this works by folding up a disk. By increasing the radius of the disk, the gap in the sphere closes up, so that in the limit that the radius goes to infinity, we get the plane, and then only a single point is needed to plug up the gap. This new point is sometimes referred to as the point at infinity. But why should we be allowed to add this point? I mean, one of the most disturbing things about it is that on the plane, it would be infinitely far away from all the other points. But then, if rescaling is a genuine symmetry of the theory, then lengths are not a meaningful quantity. So it's not a problem that the point at infinity is infinitely far away from any point on the plane. But angles should be a meaningful quantity, and so we do need to check angles are preserved when we do this conformal extension. And that requires us to 1. Be a bit more precise about how we do the extension, and 2. Define what we mean by angles on a sphere. Let's tackle the second question first. It turns out what we want to do is to define the angle between 2 curves. The reason is then we can talk about curves on a sphere. And since we view the sphere as being in 3D space, then these are just curves in 3D space. Then what's the angle between 2 curves? Well, we're familiar with the angle between vectors, so what we want to do is to get vectors from the curves, at least at the point where the 2 curves meet. This is given by the tangent vectors, and then the angle at the meeting point is the angle between these tangent vectors. And this also works with curves in 3D, and in particular, curves on a sphere. Now that we've established what angles are on a sphere, we want to return to the earlier question of how this compactification occurs. In other words, we want a way to map the sphere onto the plane, and vice versa, in a way that these angles are preserved. There is a well-known map which does this, called stereographic projection. We can look at how the projection works in a lower dimensional case, which instead gives a mapping from the circle to the line instead of the sphere to the plane. But the mapping from the sphere to the plane works similarly. The way it works is that for every point on the circle, except for the North Pole, a line can be drawn going through the North Pole and the chosen point. This line also hits the x-axis in a unique position. Sending every point on the circle to its corresponding point on the line defines this stereographic projection map. And with some elementary geometry, you can show this formula for the image of a point on the circle. Back to 2D stereographic projection. To show angles are preserved, what you need to check is that for every angle on the sphere, given by a pair of crossing curves, that if those curves are then mapped onto the plane by stereographic projection, then the angle remains the same. And if you manage to check that, then that completes the proof that the sphere is a conformal extension of the plane, i.e. it is an extension that preserves angles. Good, we have our extended plane. Now the point of us doing this extension was to look at the extra symmetry that the extension buys us. So let's look at the original transformations on the plane, rotation, dilatation, and translation, and see how they extend to transformations of the sphere. The most straightforward to understand is the rotation of the plane. Inverting the stereographic projection, the analogous transformation on the sphere is also a rotation. Now let's look at dilatation of the plane. On the sphere, it sort of squeezes the points of the sphere towards the North Pole. I've talked about this transformation on the sphere a few times in previous videos, and this is where we make contact with the earlier mention of spacetime. Now this corresponds to a relativistic effect due to accelerating upwards, which in relativity is called a boost. Finally, for relativistic videos, and this is where we make contact. I've talked about this transformation on the sphere a few times in previous videos, and this is where we make contact with the earlier mention of transformation on the sphere a few times in previous videos, and this is where we make contact with the earlier mention of spacetime. Now this corresponds to a relativistic effect due to accelerating upwards, which in relativity is called a boost. Finally, let's look at translation. This is probably the weirdest one on the sphere. It squeezes the points to the right from this point of view, starting from the left of the North Pole, but while keeping the North Pole fixed. A larger translation would in fact start squeezing the points to the right and then up back towards the North Pole. Notice that from the left of the North Pole, but while keeping the North Pole fixed. A larger translation would in fact start squeezing the points to the right and then up back towards the North Pole. Notice that for all of these, the North Pole is actually a fixed point. And this is a manifestation of the fact that the North Pole represents the point at infinity, which isn't part of the plane. Now this corresponds to a relativistic effect due to accelerating upwards, which in relativity is called a boost. Finally, let's look at translation. This is probably the weirdest one on the sphere. It squeezes the points to the right from this point of view, starting from the left of the North Pole, but while keeping the North Pole fixed. A larger translation would in fact start squeezing the points to the right and then up back towards the North Pole. Notice that for all of these, the North Pole is actually a fixed point. And this is a manifestation of the fact that the North Pole represents the point at infinity, which isn't part of the plane. So any proper transformations of the plane must fix infinity. But now that we're on the sphere, the point at infinity loses its privileged status, and we need to treat the points more democratically. In particular, we can do this translation on the sphere, but with the sphere flipped upside down. And this transformation definitely doesn't preserve the point at infinity. In fact, this transformation is precisely the special conformal transformation. In physics, these four transformations point at infinity loses its privileged status, and we need to treat the points more democratically. In particular, we can do this translation on the sphere, but with the sphere flipped upside down. And this transformation definitely doesn't preserve the point at infinity. Sphere flipped upside down. And this transformation definitely doesn't preserve the point at infinity. In fact, this transformation is precisely the special conformal transformation. In physics, these four transformations, rotation, dilatation, translations, and special conformal transformations, generate all the conformal transformations. And in fact, this process we did works for any number of dimensions, or even any number of space and time dimensions, if we talk about the conformal symmetries of space-time. Let's recap what we did. The conformal transformations of the plane are only rotation, dilatation, and translation. But since we only care about angles and not distances, we obtained a more symmetric space from the plane, called its conformal extension, which turned out to be a sphere. The sphere came from adding just a single point at infinity, and the original conformal transformations are those which preserve the point at infinity. But the sphere has additional symmetries, which need not preserve the point at infinity, in particular these special conformal transformations. The consequences of this will be explored more next time, but for now, thanks for watching. If you found this interesting, leave a like if you like, or subscribe. It helps me out, and if you have any questions or comments, leave them down below. See you next time.
So I just found out the creator of this channel has a website now. They have a website now. WikiLee. Okay. So University of York. Interesting. Focus. Interesting. What I wanted to share with you is interesting. Interesting. Interesting fella. Bang here. This is easy. Good. Ways for this. The interview and all that. Where is the CV or stuff? I don't know. Service. Okay. Interesting stuff. I just got no more deeper stuff about conformal algebras and conformal transformation. So where was I, by the way? Yeah, I was yeah, what I wanted to do about the so Angles and conformal transformations. Calculations are still pending, huh? Calculations still pending. So, let's go to this is books, Francis. F2. Mm-hmm. Yeah, this is what I've prepared. No. Ooh, this is exactly what I wanted to see, right? So, put the above function into simpler form. We define the following generators. This is cool. What? Interesting. Oh, that's perfect. That is so perfect. God, shit. This is exactly what I wanted. This is exactly what I wanted, right? You're simplifying into some. Wow, 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 wow. Fuck no. Wow, wow. This is this is beautiful. This is conformal algebra is putting in the form of a SOD plus 1, algebra, the algebra. This is so fucking good. This is exactly, you make a statement like this. Z, but thank you for the. This is nice. This is a good section. This is a good book. Wow. This is a great book, man. This is a really great book. I mean, I just like the fact that they reduced the whole conformal algebra into a very simple SOPQ algebra, SOD plus 1 common algebra. Wow. Wow. Okay, that's interesting. Chapter 4 of this book. So this book is apparently available in the library. I'll pick it up soon. Wow, this is so fun. This is nice. I like it. Wow. I mean, I don't even have to ask sir now. Exactly, right? Francisco is the way to go. Wow. Solution. Right. Simplify the conformal algebra. Conformal algebra by defining some redefining things. So you get the required algebra. Same number of generators. Francisco. Cool. It's nice. And then ठीक है. I'll distract. Okay. Annuals and translation, right? So what is 100% constant? So you can do the calculation for this. You can't just say this. We just have a slice of bread. Oh man. Should I toast? Okay. Mm-hmm. So, angles. How does this whole picture fit into angles? Yeah, I don't get the answer. Yes, I have to calculate this. Consider two vectors. Define angles between them. Wait, what? How do you define angles in a Minkowski system? Um. Uh, um. What? Oh. I think angles are more relevant again for yeah, for for what? Yeah, for Euclidean spaces. Angles of generalization is again conformal. This is then it comes what? You see. Okay, so angles can be, if you change, you can actually change the length of the vectors. Both the vectors, you can just change the length, and then the angles will still remain the same. So the metric can still be scaled by a constant, right? Scale. Uh-huh. Uh-huh. Median to scale, okay. Okay. One can actually give this a read. This is a perfect thing. It's pretty small. I think we saw this. I think I don't have to declare the field correspondence. I just have to make sure I know these algebras and I mean it's nothing. You just have to rewrite some of the algebras to make it simple, yeah? So what would that be? J mu nu is equals to L mu nu. J minus 1 from 0 equals to D. J minus 1 from mu equals to half of P mu minus K mu. And J0 comma mu is half of P mu plus K mu. So your J is now AP and JAP minus JAP, taking values that will be belongs to from minus 1 to D. Usually you take from 0 to D, right? Now add a minus 1 to it. Do it. plus 1 damage. Deepest dimension. Previously 1 to D. This is 1 to D. Mu comma V to D. Yep. Function of 0 add किया. D plus 2 dimension हो गया अब. And now it obeys it. So D plus 1 comma 1. Yeah, algebra. So these are isomorphic. Now what is the D comma 2 doing here? What the fuck? Interesting. So D comma 2 apparently is isomorphic to so D plus 1 comma 1 or what? Okay, that will be for some other time. Now yeah, so this is kind of exploratory thing. Yeah, that will remain purple. My cartoon map is not. These are more important for those things. So not, yeah, these are exploratory stuff. You know, exploratory. We call the method of images and how this falls into that. How Laplace equation and intrinsic length scale. Okay, I know I'm skipping a lot of stuff, but these are important. Yep, I need to take a break. Unfortunately, this will be the. I mean, actually, you can add part 2 to DCCS. Yes. I need to take a break. So add 15 minutes to this. So say 30 minutes. I mean, not sense, but still. Blah blah blah. Anyway, there is this, these, which I'm not going to go there yet because I need the breather, and I don't think I'll come soon after the breather. Or should I? Wait. So what's left? These stuff, and I need a breather of what happened here till now. Right? I need to process things. This will be the part 1. Yep. DCCS part 1 is now done. See you in part 2. Sure. Before that, let me just process it slightly. Yeah. Let me process slightly. So what happened is we found some good resources of this, and good resource of Francesco's good book. Also suggested, and I'll ask couple of friends about these few doubts, and I need to I know I need to kind of fix this, but you should also read DCCS and anti-DCCS space wala part. So just thinking, should I do a DCCS part 2 or go ahead with the anti-DCCS part? Yeah, these are few theoretic stuff. Yep. So that will be a good stop from these. I'll group this into field theoretic stuff. theoretic stuff, which I will them later, but later when I come back to the field theory approach. Until then I can just remember to do it easily.